How do we analyze our results? Okay, your warm-up today was in your notebook to write what is precision, what is accuracy, and what does quantitative mean? What about qualitative? Then we had a discussion about the difference between precision and accuracy. Okay, we went over this a couple of different ways in class. So sometimes we talked about playing darts. For accuracy, we wanted to hit the bullseye. We wanted to be on target. Okay, so this was like if we had a cop and he had a radar gun. He was sat by the side of the road, and every time a car drove by at 60 miles per hour, that's what his gun would read. That would be the reading. All right, so that would be accurate. But what about if he hadn't calibrated his radar gun? And then every time a car actually drove by at 60 miles per hour, the cop read 65 miles per hour on his radar gun. So while it's not an accurate number, it's not correct, it's not close to that correct value, it is precise because he keeps getting the same value in the same situation. Okay, then we talked a little bit about quantitative versus qualitative. Quantitative just means that we're dealing with numbers. As someone pointed out, that N in quantitative is one of the differences in those words, and so it has to do with the numbers. Whereas qualitative deals with the qualities or the characteristics of an object. Okay, we then also talked about sources of error, but I already covered that in yesterday's video on lab design. Okay, we talked a little bit about what analyzing data actually means. What it really means is just looking for patterns. And today we're going to figure out one way to do that. Okay, so we're going to start with finding a proportionality. We're going to look at each column separately. And then what we're going to do is we're going to take the first number, okay, and we're going to call that the first number. So we're going to say that's times 1 to get to itself. There we go, times 1. Okay, what we're going to do next is we're going to look at the second row. And we're going to say, okay, what did we have to do from that very first row to get to that second data point? In this case, we just multiplied by 2. Like that. Okay, so I think for the rest of this column, the pattern's pretty easy. For the third row, we multiply by 3, the fourth row by 5, etc. Okay, there's the first column done. So we're going to do the same thing with the second column. So the first row, I'm going to say, okay, I multiply by 1 to go from 28 to 28. Okay, so now for the second row, to go from 56 to 28, to go from 28 to 56, you had to double it. So another way to do this, when it's maybe not quite as easy of a pattern to see, you could take the second row, 56, and divide it by the first row, 28, and the answer you get is 2. So if you divided by 2 going back up the table, you had to multiply by 2 going down the table. Okay, so again, going down this column, 84 divided by 28 is 3, 112 divided by 28 is 4, and the pattern is the same on this side as it was on the previous side. Alright, so now, looking at these numbers in red, we're going to ignore the actual data for a second. Alright, for both the time column and the distance column, those numbers are the same. So in this case, each one of these data points provides a proportionality. The ratio of any of those two numbers is the same. So in this case, we're going to say that these are directly proportional. Okay, let's try that again. So this time, we're going to do something a little bit different. All right, so in this case, I'm going to do the same thing, and I'll just put it up here. Okay, so you'll notice right away that this is a different pattern than before. All right, I'm going to point out one of these because in case you were following along, the 5th data point down, the number is 0.013. Now, if I take that and divide it by 0.2, I don't get exactly 15. All right, or exactly 1/15. So, but I think you can probably put in 1/15 in your calculator and then multiply that by 0.2 and see that you get 0.013 repeating. So our data is not always going to be perfect. Sometimes close enough is going to be good enough here, just looking for patterns. Okay, so you'll notice, all right, that for each data point, all right, that the multiplier on the left is the inverse of the multiplier on the right. Okay, we would say in this case that frequency and period are inversely proportional. All right, so here's the first sample problem that we did in class. Okay, so this was on your handout. All right, so here's the answers that we came up with for our multipliers. Okay, so here's another case, like the very first example, where the multipliers are the same. So if I was going to ask myself, what must I do to the second variable's multiplier, in this case x, to get the first multiplier, so for y? Since they're the same, I don't have to do anything. All right, that means that we are going to say that y is proportional to x. That's what that little symbol down there means. Okay, sample problem 2. All right, we also did this in class, okay? So in this case, when we got the answers, a was proportional to b squared. In sample problem 3, when we followed along, all right, for force, all right, so then it was times 1 times 1/4, 1/9, 1/64 approximately, and 1/900, all right, and then in the R column, each number, since the first number is 1, was just itself. Each multiplier was the same as the number. So in this case, we had to both take the inverse and square it. So we would say that f is proportional to 1/r squared. Okay, then you guys practiced, and we talked about how this was making a linear correlation between data that wasn't necessarily linear to start with. All right, here are those 4 graphs, and hopefully this color shows up a little bit better on your computer than it did on my smartboard. Notice that all these proportions are in the same format, but just with a different exponent. So eventually, we're going to use these graphs to make equations. So if we linearize the data, we can graph it, either with the calculator, Excel, by hand, whatever. And then we find the slope of the best fit line. And sometimes we'll find the y-intercept. Obviously, if it's an inverse relationship, there isn't one. All right, and then we'll make an equation. So that's how we'll go from this proportion that we've been working with to an actual equation. And that's how we'll get the formulas and the equations that we'll use in class. But we'll do that when we actually have data, and then it'll be more meaningful. All right, so this is just some information. We'll come back to this when we actually do it. All right, when we did proportions in geometry, there was this thing called a scale factor that was the multiplication factor that you use to go from one ratio to the other. So that's kind of the same thing here, k. And we call that the proportionality constant. Usually we're going to start off with the assumption that the y-intercept is 0, although that won't be true in a couple of cases in this class. And please just remember, we'll worry about this later when we have some lab data to make it make sense. All right, don't forget your homework tonight is to play with the equation grapher at the end of section 1.1 of OpenStax and do the 3 practice problems. I know they're a little bit more difficult than what we did in class, If you get fractions that are a little bit funny, try to give them a common denominator and see if that helps. Remember, if you get stuck, I want to know what you did understand and where you got stuck so we can go on from there. Also, your pre-test is still out there and the mastery quizzes are still open. You did a reflection in your notebook of what you learned today. If you want to go back to that while you're doing your homework, I recommend it. Hopefully it helps.